We have to work out the voltage drop for R1 because that's where your total current is passing through, the same as the total current passing through here. So we know the total current, we know our supply voltage, and we know the value of R1. So the voltage drop across R1 is your total current times the resistance of R1, as you can see here, 7.06 milliamps times 1.5k, and the voltage drop across right there is 10.59 volts. So that's how much voltage we're losing just in that area there. Now the remaining voltage should be across your parallel resistors. So if we work that out, we've got the voltage across R2 in parallel with R3 in parallel with R4, so we're looking at this branch here. Is equal to the supply voltage minus the voltage drop across R1, so 10.59 volts. So we've got 12 minus 10.59, and we'd end up with a voltage of 1.41 volts. So that's all the potential that's across these three resistors. And once we know that, we can even go on further, and then knowing the voltage drop across the parallel branches in both cases and the value of the resistance, we could work out the current flow through each branch as well. So what we've done here is just gone through and we've worked out the current situation for this circuit here. We came up with a voltage of 5.37 volts, which we'll call VP, so basically your parallel voltage. And from that we can now work out what the current passing through each of these resistors here. Now remember that we've got a current leaving the battery and it's splitting here, recombining, and then coming back to the battery. So for R2, the current through R2 is equal to your parallel voltage divided by your resistance. So we've got 5.37 volts, which is what we worked out here. We've got 3.3k, and we end up with 1.63 milliamps. So we've got 1.63 milliamps passing up through that branch, and for the current through R3, this resistor here, we've got 5.37 volts. It has to be the same voltage as this one, but this time we've got 6.8 k ohms, and we end up with 789.71 microamps passing up through here. Now, as a check, what we can do, because we know what current's leaving the battery and we know what's passing through these resistors, and we add all that up, it should come back to your total current. Now total current is 2.42 milliamps, and if we add the current through R2 plus the current through R3, we should end up with IT. So 1.63 milliamps plus 789.71 microamps is going to give you close to 2.42 milliamps. It's slightly short, but it's just rounding errors when you're doing the calculations. Now for this circuit here, again, we worked out our voltage drop across our parallel section. We came up with 1.41 volts, and we call that VP. And you can see here for R2, or the current passing through I2, you got your parallel voltage drop divided by R2, you end up with 427.3 microamps. We've done the same thing for R3. We've got 6.41 milliamps, and we did the same thing for R4, and we ended up with 207.35 microamps. And if you add all those up, you end up with a value very close to 7.06 milliamps, which is what our total current is. And that's just a check, to see if your calculations are right. The interesting thing here, because we've got a much lower resistor than these two, you can see here that the majority of current is passing through the 220 ohm resistor, and you can see here that the R2 value would be higher in current than the R4 the R4 value because of the high resistance in this area. This is the second circuit that we had up on the board. You've got a 1.5k and this is in the negative rail, and then we had our 3.3k, 220 ohm, and then 6.8k, and these are in parallel. As you can see here, they're all coming off right the negative side and they're all attached to the positive side. So what we'll do now is we'll just do a measurement of the total resistance and see if that comes up close to what we calculated, and then we'll do a measurement of the parallel resistance and see if that comes up close to what we calculated. So measuring the total resistance, we should have about 1.7k, and as you can see here we're getting 1.69, and again taking in the tolerance values of the resistors, so that's pretty close. And taking in the parallel right combination with the three resistors here, that should be close to 200 ohms, and we're getting 200.34. So again, you can see that that works with the calculations that we did on the board also. Alright, so we've got the circuit here. We just applied voltage to it. We had to use a different power supply because the other one didn't quite get up to 12 volts. But if we measure across our inputs here, you can see on the meter that we're getting pretty close to 12 volts without messing around too much, so we'll use that for our supply. So the voltage drop across VR1, which is 1.5k ohms, should be around about 10 volts, and it should be 10.59. we're getting 10.67, so you can see that the calculations and the measurement are pretty close again. As we mentioned many times before, it's just the tolerances of the resistors. And if we go across the parallel circuit, we should end up with 1.41, and we're getting 1.435, and again taking into consideration resistor tolerances, that's where you're getting your difference from. So 1.4 is pretty much spot on to what we calculated. So I've just connected it up so we can actually measure the total current that we calculated. That should be around 7.1 milliamps or thereabouts. So if we put the power on and we just look at the meter here, we can see that for our 12 volt supply we're getting 7.18. I've just rearranged the circuit slightly, but we've still got the same configuration. It's just that I've put links in so I can break into each of the parallel resistors and get a measurement of the current. And the first one we're going to have a look at is the 3.3k, and for that one we should have had about 427 microamps. And I'll just connect across our supply to that resistor. So we've got 427, we've got 429 microamps. So you can see there that we're pretty close to what we calculated on the board. So I'll put the link back in for the 3.3k ohm resistor. I've taken the link out for the 220 ohm resistor, and for that one we should have about 6.4 milliamps. So we'll just check that one and see if that's what's happening in this area. And you can see here we've got 6.5 milliamps, and again that would be close to what we calculated, and again taking into consideration the differences in the resistor tolerances. So just recapping, I've just put the link back in for the 220 ohm resistor. I've taken it out for the 6.8k, so now we can measure the current to the 6.8k resistor, and that should measure around about 207 microamps or thereabouts. We'll see what we get there. And we've got 207 microamps, so pretty much spot on. Yeah, that proves our calculations on the board, and our practical matches our theory.